Hello, everyone. Thank you for joining us today for this webinar titled Intro to Composite Testing Standards and Methods. It is brought to you by Composites World and presented by Instron. My name is Ginger Gardner, and I am Senior Technical Editor at Composites World. Composite materials offer exceptional performance and design flexibility, but their complexity introduces significant challenges in testing and validation. Accurate and reliable test data is essential for material development and structural design, especially in safety-critical industries such as aerospace, automotive, and wind energy. This webinar will provide a comprehensive introduction to composite materials testing, covering the full spectrum of mechanical tests required for static characterization. Attendees will gain insights into industry standards, equipment requirements, and best practices for ensuring compliance with auditing bodies like NADCAP. Instron will also explore testing methods such as compression after impact, CAI, Shear, and Flexure testing, and will also discuss emerging trends shaping the future of composite testing. Our presenters today are Stefan Botsky and Ashley Davis, both Senior Applications Engineers for Instron. Stefan Botsky specializes in high-force static testing of composites and other advanced materials. As a key member of the ASTM D30 Committee on Composite Materials, he brings deep technical expertise and industry insight to every project. His work bridges rigorous standards with real-world applications in materials testing. Ashley Davis is a mechanical engineer with a dynamic background across quality assurance, automation, and business development. As a senior applications engineer at Instron, she brings a multidisciplinary perspective to the testing of composites and other high-strength materials. Specializing in static high-force testing, Ashley combines technical expertise with real-world problem-solving to support critical applications across advanced engineering industries. Before we begin, I'd like to remind you to please submit your questions by typing them into the Q&A panel on the right hand of your screen. We will get to those during our Q&A session at the end of this presentation. And now I'm going to hand it over to Stefan and Ashley.
Thank you for that warm introduction. Thank you, everybody, for joining us today. I think we have a first poll on the opening slide on the amounts of, or the many different tests that you're running. Can we run that poll, please?
It is up right now, Stefan.
Okay, thank you very much.
So for how many different test types, it looks like 56% are 1 to 5 different test types, 24% 6 to 10, and then 19% of people are running 11 plus different types of tests.
Thank you. Very interesting. This is our agenda for today. We're going to start out by looking at composite material properties. Then we're going to move into an overview of composite testing. So that's the part where we talk all about the different types of tests and testing standards that you most likely need to follow. Then we're going to look at all the different challenges, or most of the different challenges that are associated with that kind of testing. And then we're going to look at some future trends before we move into the Q&A section of our webinar today, where we try to answer as many of the questions that you're submitting today as possible. I wanted to start out with the ASTM 3878, which is the standard terminology for composite materials. So this is a standard that the ASTM D30 committee is working with, and it is full of all kinds of definitions that are related to composites and composites testing. And I want to start out by looking at what does the ASTM D30 committee actually say a composite is. So a composite, the material now, is a substance consisting of 2 or more different materials insoluble in one another, which are combined to form a useful engineering material possessing certain properties not possessed by its constituents. So basically, a good analogy for this is usually if you think about concrete and rebar. So you put the rebar in and you pour the concrete, and they're insoluble to one another, right? So the materials, they get combined, but they're not like a metal alloy where you can mix in other metals and they kind of become a new kind of metal, but they're soluble in one another, right? So composites, you keep the different materials apart, like they're combined, but they're not soluble, and then they usually give you properties that are not possessed by the individual ones. So we're dealing with multiple materials that we try to combine. We're going to run another poll on this slide and asking you about the matrix materials that you're using. So we're going to move into now here so we established there's 2 different materials. You could also say 2 distinct phases, and we break that up into matrix and then the reinforcement within there. And the end applications, there are mostly aerospace that the materials that we're talking about today are going into, but there's also some adoption in the automotive industry, in a renewable energy industry like wind energy. The wind blades are typically made from composites, and there's a couple other industry, of course, where there's some adoption. So the most common matrix materials that we're dealing with are polymer matrix composites, by far the most common one that we see at Instron that our customers need to test. But there's also, for ultra high temperature applications, for example, ceramic matrix composites are, I would say, grow quite a bit right now. And then there's also metals matrix composites. And there's also many natural examples like wood, for example, that you can use here. So did we get any results on the poll yet?
Yeah, so we're looking at about 58% use thermoset, 31% use thermoplastic, and then 12%, so pretty small, are using other, but it's definitely dominantly thermoset.
Thank you. Yeah, and that's still kind of expected, but we definitely see the trend towards more and more adoption of thermoplastic composites. So very interesting. Thanks for entering in our poll there, giving us some insight in what you're actually using. Now, the other component we need to talk about is the reinforcements. And you can kind of break these down by their shape and form, for example. So you could have just little particles that you mix into your plastics or your other types of matrix materials. You can have short chopped fibers, for example, like you see here in this example. Or you can have continuous fibers that kind of go through the whole, what we call a ply. Each individual sheet here you call ply, and then they get laminated together. And you can see the fibers in these are continuous all the way through and are typically oriented at a certain direction. So we can break it up between discontinuous and continuous fibers, and then of course also in the material itself that you're using. So maybe you're using carbon fiber. We see that, of course, a lot. And then glass fiber, but there's all kinds of different fibers and also different resins. All of these are always evolving, and there's new composites made with new materials and new ways of combining the different materials. We see a lot of natural fibers and resins now being adopted, and people trying to make composites out of those, which then also makes it more like you have kind of renewable materials there, and recycling also becomes much more feasible. Now we want to look at the bulk properties to understand like the key differences to more traditional materials. So if we look at like metals or plastics, they're considered to be isotropic, which means their properties are kind of independent of the direction that, for example, you would apply a load. Like if you imagine this piece down here to be a piece of metal, it doesn't really matter in which direction you're pulling or pushing on it. It will have the same kind of strength in all directions. Composites, on the other hand, are considered anisotropic, which means that their bulk properties vary strongly with the direction that you apply a load. If we take this example down here, the black dots are supposed to be the fibers, and then the lines kind of show you in what orientation they are oriented. So we're talking about continuous fibers, and they are all oriented in this example here in direction number 1, which will also be the direction in which the material has the highest strength if we were to apply a tensile or compression load in that direction. And then in direction number 2, it would be much like dramatically much weaker if all of the fibers are aligned in this way. Direction number 2 will be very weak, and it will basically only be the strength of the matrix material and how well that is bonded to the fibers and how much strength that can carry, but the fibers themselves cannot take any of that load. And then there's also direction number 3, which is considered the through thickness direction. So direction number 1 and 2, they're typically defined as the in-plane directions, and then direction number 3 is the through thickness direction. And as you've seen in the previous slide, you usually have multiple stacks that get laminated on top of each other, and that's how you end up with your composite, which is also the reason why the interlaminar fracture properties are very important for composites, because you laminate them together. If there was a crack or other failure, a void or something like that in between, you need to know how much residual strength is in your composite. So it's not just the normal tensile compression shear. There's a lot of other test types which we'll get to. So since the strength of the material is heavily dependent on the on the application of the load, like where and from what direction you're applying it. You need to test your materials in tensile in all kinds of direction. You also need to determine the modulus in the different directions. And then the same is true for compressive strength, because composites typically are much weaker in their in compression than they are in tensile. I like to kind of use an example. If you think about a cooked spaghetti and you pull on it, it will have some kind of strength, right? But if you start pushing on it, it will just buckle, and there's like not really any force that it can hold. So the compressive strength of a composite is typically dependent on how well the matrix material can prevent the fibers from buckling. So you're still going to have quite a bit of strength in compression, but it will typically be much lower than tensile, about a third. But it really depends on the fiber orientation and the different materials that you're using to make your composite. And then in shear, you need to test all the different combinations of directions as well as the modulus determination in those. And then the same is true for Poisson's ratio of composites. Now, moving on here a little bit to the other side of the slide, another thing to keep in mind is that humidity and temperature will affect the strength of your composite materials. So they do take up moisture, which is also for why you need to simulate that. You need to typically condition your specimens if they are in a humid environment. So you need to condition them before you test them. And then you also need to simulate the different high and low test temperatures that your composites are supposed to be operating in. So it really depends on your end application and what kind of conditions will they see there, and then to simulate those. Now we're going to move on into the overview of composites testing. So we're going to start out here in the testing pyramid. On the bottom is typically where Instron plays here. So you have the individual resin materials, you have the individual fiber materials, then you start combining those into the coupons, and you need to test those when they're together and then in different fiber orientations. And then you might start putting them together to smaller elements which need to be tested. This is like where you kind of establish your databases for your materials. This is typically where Instron plays. And the most common tests that are being run down here are tension, compression, shear, and flex, as well as a range of what we call structural tests, like on coupons with open hole in tension or in compression, because fasteners are still used to combine or to connect individual parts of composites. And you also need to therefore simulate bearing loading as well as testing compression after impact. So there's a bunch of structural tests that you need to run, but also much more traditional ones. Tension, if the fibers are oriented in the 0 degree or direction number 1 in our example, that is a fiber dominant property. And in the 90-degree direction, that is, as mentioned earlier, the matrix and fiber matrix adhesion property. And in compression, it is really dependent on how well the matrix, how good it can prevent the fibers from buckling and the adhesion qualities between the resin and the fibers. And shear is a matrix dominant property, and really kind of depending on how well the shear stresses can be transferred across the composite material, and then flex is a combination from all of those. Here's a video of a typical in-plane tensile test. So we're testing in direction number 1 or in direction number 2. And you can see here, this is at the end of the test. I'm going to replay this here one more time. You have fibers and parts of plastic flying around. It can be quite spectacular breaks. But you also need to keep in mind here now the challenges that come with that. Of course, operators need to be careful removing the broken parts of the specimen. You wouldn't want to touch any sharp parts and get carbon fiber and plastic kind of in your skin, right? So that's definitely something to keep in mind. You need to make sure that you keep your test equipment relatively clean and make sure that you clean up those fibers afterwards. Here's another video that we recorded. It's also in plane tensile testing, and this is now a unidirectional material. So all of the fibers are oriented on the vertical axis, and this is recorded with 10,000 frames per second. And even with that, I'm going to start playing the video now. Even with that high resolution, it's pretty much impossible to tell when the break actually happened. It just kind of explodes once that maximum strength is reached. And what you also can see very clearly in this video, there's also a lot of dust and like really, really fine small particles. So you need to make sure that your equipment is protected from that, because carbon fiber is electrically conductive. So if that gets into your electronics, it will harm your test frame, but also, of course, make sure that your operators are protected from that harmful dust and debris. So in plane tensile testing, most common standards we have here are definitely ASTM D3039 and ISO 527-4 and 5, but there's also a variety of more what I would call legacy standards that some people still test to. So like we established earlier, specimens can have a variety of layups with fiber orientations, either in the 0 degree and the 90 degree direction, or something more balanced like we've seen in the first video. So that's when you stack different plies on top of each other with different fiber orientations to get something that is more balanced and probably something that is much more realistic for end applications. We typically deal with tapped specimens. It's really interesting to see the poll results because thermosets are still clearly the most used matrix materials, which also kind of helps with this because tabbing does prevent damage to fibers from the jaw face when you engage your grips to the specimen. And you can grip them, you can grip composite specimens that are tapped with a range of grips that are either manual or hydraulic and with normal serrated faces. But tabbing is really time consuming, it's expensive, and it can also be really, really difficult. It's really kind of a science, and there's some really good material out there on Composites World magazine to help you with that, to kind of get you started on that. But some materials, like we've established, a lot of you test thermoplastic composites, and they typically have a very low adhesion quality. They are chemically inert, and they have a couple other characteristics that make it really, really hard to bond things to it. So you might not be able to have any kind of tabs on thermoplastic composites. What we usually do there is we grip those with jaw face patterns that are very fine. We also use carbide coated faces, which can give you good results. And I also would recommend trying out simple sandpaper or emery cloth that you can use between your jaw face. Still, I would recommend a finer pattern, not necessarily serrated, and you use the sandpaper in between there to kind of give you that grip so that your specimen doesn't slip, so you can get away with like just enough gripping pressure, initial gripping pressure, but at the same time protect your specimen from being cut into. There's also good recommendations in ISO 527-4 and 5 on this in the latest revisions. And then lastly, here on the in-plane tensile testing, we have protruded unidirectional materials. They're very important. They're typically in the form of round rods. They're very, very strong in their axial direction, but in the transverse direction, they're very, very weak. Like we established unidirectional materials, all the fibers oriented only in one direction. So if you start clamping on from the side, that can be difficult and you might damage your material there. So a common solution to that is using a very long grip engagement length. So you try to grip it over a long, long distance and use a semicircular grip profile that matches the test specimen's diameter. Here's another video of a typical in-plane tensile test. And you can see here, we're going to slow this down a little bit. And you can see there's even sparks flying from the knife edges of the extensometer when it gets when the specimen explodes, and then the extensometer kind of goes flying and the knife edges rip along the specimen. So very hard surfaces and very challenging to record strain, as you can imagine, with these kinds of materials. But nonetheless, very spectacular breaks. So now we're going to move on to compression testing. We're still in the in-plane direction, so direction number 1 or 2, and we're using end loading to initiate the force into our specimen. Most common standards for that are ASTM D695 and ASTM D6484. Kind of looks like this. So you have guides around your test specimen, which is the black part here in the middle. And like I said earlier, the force is being initiated at the ends of the specimen. So you get some force here. Typically, you come down with a compression platen from the top, and then your specimen is supported on the bottom. You can also run this test with this test fixture with a tapped specimens, which would kind of look like this. The green parts here are supposed to show the tabs of the specimen, and then you're running a free gauge section down here in the specimen, but still supported by the guides of the fixture. So you can kind of see it here, the anti-buckling plates, and then your specimen here in between them, in between the anti-buckling plates, and then they get connected to the base support, where then your specimen rests on the bottom here of the base support, and it will stick out of the anti-buckling plates ever so slightly on the top, where you then apply the load coming down with a compression platen. And then for the ASTM 6484, that is a open hole compression test, which can be run either in end loading or in shear. So you can also use this fixture in shear, but this is here the method where you're running it in end loading, where you have these end parts here. These are not compression platens. These have the shape where the fixture fits into, and then you still put that in between compression platens, and you can load your open hole specimen in compression that way with end loading. Now we're going to move on to the next category, which is still in-plane compression testing, but now we're initiating the force into the specimen with shear. Most common standard here is the ASTM D3410 and also ISO 14126, and there's also a couple other standards from Airbus, for example, that run compression like this. So now the difference is here, you're using tapped specimens typically, and then you initiate the force here from the side. So you clamp onto your specimen with either a test fixture, something like the Itery fixture that you can see here from ASTM D3410, and also allowed in ASTM 14126. So you're clamping on the sides, and then this gets driven together. So either you come down here with a compression platen on the top on the fixture and compress it, or if you run it like the Airbus standard, for example, allows hydraulic wedge grips that you use with load introduction plates in between your gripping and your specimen. So you clamp on the sides of the specimen and then drive the crosshead down, and then you initiate the compression like that. But it is through shear, not through the ends of the specimen. So this will also give you different results. So they're not comparable to the end loading results. And now moving on to what I would consider most common, most popular in-plane compression test, which is the combined loading approach. So we're using both of those techniques that we saw on the previous slides. And the by far most common standard for that is ASTM D6641. And we also now, in the most recent revision of ISO 14126, it does allow this fixture to actually cut out the end loading and now allows shear or combined loading in compression. And that would look kind of like this. You can use either tapped or untapped specimens, and then you have a clamping force from the sides onto your specimen, and then at the same time also some end loading. So you're initiating the load with both techniques at the same time. And this is how that fixture looks like. So you have a bottom part with guide columns and then a top part, and you put your specimen in between. And then the surfaces here, the inner surfaces of your specimen, are very much, they're very rough surfaces to give you nice coefficient of friction, so you don't have any slippage, and you make sure that your specimen is on a flat surface when you insert this, to make sure that you get that end loading portion on the bottom, and then the same on the top. You need to make sure that the end of your specimen and the ends of the top of the fixture are perfectly flush. And then combined, it kind of looks like this between compression platens, and you would start compressing. And then the shear force comes through the torquing of these 8 bolts here. You have 4 in the upper part of the fixture, and you have 4 bolts on the bottom part of the fixture. And that's where you're initiating the shear forces into your specimen. We did run this test on one of our testing machines. You can see here we ran this on a floor model machine. We had hydraulic wedge grips installed. We did not want to remove those, so we utilized adapters, piggyback adapters, to then connect our compression platens and then put the fixture in between the platens and ran the test that way. And this is how it looks like when you have a tapped specimen in there. This is close up now before the break, and then here on the right side you can see the specimen, how it looks after the break. We also have a quick video here, so I'm going to give you a quick introduction here before I started. You're going to see this sped up in the beginning of the video, and then it will slow down right before the break. So when you see the fixture actually coming down a little bit, that is, a lot of seating in the specimen and also some of the compression going on, and then we'll slow it down right before the break. So you can see kind of the compliance and the seating happening here, and then at the end when the break happens. So that's what a typical ASTM D6641 test looks like. You would run this test if you follow the standard and you determine the modulus and basically all the results that you need, you do have to use bonded strain gauges, which would kind of look like this. You need to use them on both sides of the specimen. This is how that looks like, and you get your lead cables here on the bottom coming out and here on the top. And then you need to load this into your fixture, which, you start on with the bottom part. You got to be really careful here with the lead wires of your strain gauges so they don't get damaged. And then you put the top part of the fixture down. And again, be really, really careful with the cables, but also be really, really careful with your fingers, because it's, you can definitely pinch your fingers here in between the fixture parts. All of these parts are relatively heavy. It's very solid metal. And when you insert the top part, you need to have some amount of torque. Otherwise, it will just kind of come falling down. So you need to find kind of the sweet spot where you can safely insert the top part of the fixture. Like I said, it's relatively heavy, so it can be kind of tricky. So before you load it with a specimen with attached strain gauges and wires, I would say, try the specimen out by itself without any specimens, and then maybe with some simple non-strain gauged specimens to get a feel for it, to get some experience before you start loading expensive specimens that are strain gauged. And then this is how it looks like when you have that installed in your testing machine. You got to make sure the wires come out the front, and then you can run your test. Now we're going to move on to some shear testing. We're going to look at in-plane shear. So we're still in direction number 1 and 2. Most common testing standards here are ASTM D3518, and then there's another variety of other shear tests that you can run. So in-plane shear, there's the 3518 test right here. So you're using, it is the same as D3039, but your specimen actually has the fibers oriented now in a plus and minus 45 degree orientation, which then kind of gives you a nice shear failure like you can see down here. Now it's important to note though that this is not a pure shear force that you're recording. There's always an actual tension component in there. So this can give you a good idea on your shear strength, but you're not really able to use that result as like a shear property. For that, you need something like this, which is the V-notched shear methods, ASTM D5379 and ASTM D7078. So these utilize a V-notched test specimen. So you have these V's cut into it, which is a complex specimen. This is really difficult to do. Like even rectangular coupons are more challenging than traditional materials. And now you need to kind of make this V-notch specimen. And then for the 7078, it's kind of similar. So that can be pretty tricky. But this gives you a pure shear state in the middle of the specimen. So this is really pure shear strength. So that is what you need to determine that. And you can see a typical shear strain distribution recorded with digital image correlation. And then if you have maybe very large shear strains, then you could utilize the test method ISO 20337, which allows you to test the shear properties of specimens that have larger shear strains above 5%. So these test methods typically can't provide that. So you would need to use this one, which again is a expensive specimen preparation. And it's a really complex test and a complex fixture. So I would say nothing in composite testing is really like straightforward compared to like traditional testing. But this one's definitely not the simplest. Now moving on to interlaminar shear testing, ASTM D2344 is very popular, and we also have ISO 19927 and also other standards. It's we're by no means all the standards. We're just mentioning the ones that we see the most popular ones. So you can run this short beam shear, which is basically a 3-point bend setup, but you're using a very, very narrow separation on your supports on the bottom, and then the yellow part here is your test specimen. So this is a widely used QC test for materials and parts, and you can use a simple rectangular specimen. You can, however, not determine the modulus of your shear interlaminar shear modulus with this testing. For that, you would need something like double beam shear, which is the ISO 19927, which you can then use a LVT or a plunger down here to determine your it will give you true interlaminar shear strength, and you can determine the interlaminar shear modulus as well. And you can kind of see the failure right here on the side in between the specimen. So that's how interlaminar shear testing looks like. Now we're going to move on to flex testing. Again, there's a huge number of testing standards that cover this, and it's like the interlaminar shear, but now we don't want shear forces. We want to minimize them as much as possible, which is why we use a different ratio of length of specimen to thickness. So we make that much larger, and you basically just use a simple beam loading technique here. You can run this in either 3 or 4 point application. So you have 2 supports on the bottom, then either have 1 loading nose coming down, or in this case, like you can see here, 2 loading noses come down, and you can determine the modulus in the 4-point bend configuration, which does require, again, a measurement of the deflection right down here under the specimen. Then there is the through thickness direction. So through thickness, tension, and compression. And there's different methods. This is the direct method, and ASTM D7291 covers this, or ISO 20975. So the specimens are typically cut from very thick laminates, and it allows you the determination of the modulus, Poisson's ratio, and the strength. But you do require, again, strain gauges. Like for many composites tests, strain gauges are required to determine the modulus and the Poisson's ratio. So you usually have a stud that you can pull on, and then you adhere your specimen to it. So you take your thick specimen and you glue it to the studs on the top and on the bottom, and then you apply the loads here and pull this apart in tension, and then you want the failure to happen somewhere here in the middle, and that gives you a through thickness now. So in the through thickness direction gives you your tension and your compression strength, and these are the direct methods. This is the ISO 20975 in tension on a testing machine, and this is how it would look like in compression with the 2 platens coming down. You can see here the strain gauges being connected to the specimen to determine the modulus and the Poisson's ratio. Now moving on to through thickness tension with the indirect method. So there's an there's an Airbus standard that covers, but there's also ASTM D6415, which is being revised. I think it's being revised right now in the committee. And this is a curved beam indirect method. So you have a through thickness tension stress in the corner up here. So this gives you the through thickness tension. And it gives you failure strength, but you, again, cannot determine the modulus with this test method. It's suitable for thin laminates as well, and it needs a special specimen and fixture, though. So you put your specimen through, and there's the support rollers here on the bottom. You have the loading noses coming down here, and you kind of come down with it, and which then, like you can see here, the force application on the top and on the bottom, which then gives you a tension stress right up here in the curve of the specimen. But again, not possible with this to determine the modulus. Want to look at interlaminar fracture toughness here as well. So ASTM D5528 for the mode 1 opening is by far the most common. There's also mode 2 and mode 3, and then there's a mixed mode bending. They kind of look like this. So the first one here is the G1C test for the mode 1 tensile opening. So you have a double cantilever beam specimen that you can see here, where you have a crack initiation. You typically kind of force that. The testing standard explains it, and then you start pulling this apart, and you need to determine the fracture toughness as the crack grows through the specimen this way. And then in the mode 2, it kind of looks like this. It's basically a 3-point bend setup, but you have a shear crack up here, and then try to grow it through. And then this is the mixed mode bending fixture. We kind of do both at the same time. And then moving on to bearing load testing. So if you use fasteners to combine different composite materials, this is something that you'll have to simulate. So there's different Airbus standards as they are using this technique to combine composites on their airplanes. And then there's also ASTM standard and legacy standards from EN that cover these test methods. The specimens have a hole, and then you have a pin or a bolt with which you're loading it. So you put that into into that hole that you initiated in your specimen. And then you apply averaging extensometers on both sides. And it's important to understand here that bearing strength is not a material property, as it changes with the size. So the size of the hole does change your bearing properties. And down here you can see some typical failures. You need to make sure with this test method that you have the failure actually in the hole. And there's a couple of different allowables, which is really typical for composites testing standards. They typically have a variety of allowable and not allowable failure modes. So always check that. That's like, if you don't get the right failure mode, you're not in compliance with the standard. And now compression after impact, another one we need to look at here. So you have a failure from something like an impacting at this location. It might be visible, it might not be, but that doesn't mean that you don't have any interlaminar cracking or other kind of failures from that impact. So you need to simulate that, which typically looks like this. So you have a plate which you impact with a known force, usually done on a drop tower. So you can see here, this is the drop weight on the vertical axis coming down. And then this part down here where your specimen is clamped onto is down here in the specimen. And then you impact that with a known force, which then you can record, of course, with the drop tower. And then you go a step further and you take that already impacted specimen and you put it in a test fixture, depending on the testing standard that you're following. Again, there's ASTM standards, there's Airbus and Boeing standards, as they need to simulate this. And then you compress that fixture with the already impacted test plate, and then it gives you the residual strength of your composite after it has been impacted. This is typically done to simulate something like a tool being dropped on an airplane wing or something, or maybe a bird that unfortunately hits the plane. So you need to make sure that if an event like that were to happen, that your material still has enough strength left to carry all the loads and not fail in operation. Okay, so with that, now I'd like to hand it over to Ashley for the testing challenges part of the presentation.
Yeah, thank you, Stefan. So now we're going to spend some time talking about some common challenges that we see when testing composites. So in the top right, we'll indicate the challenge that we are focusing on. We're going to focus a lot on alignment. We do typically see a lot of challenges within alignment of our load string. So in the center of our slide here, we have a typical load string with the load cell and some hydraulic wedge grips. And we're seeing two of our common cases of poor alignment, somewhat extremely. But on the left, we are not coaxially aligned. So this is causing an angularity error. Our top grip is not parallel to the bottom grip. And what happens is that our specimen is actually bending, and we're creating a positive strain on one side of the specimen and a negative strain on the other side of the specimen. And I'm going to typically refer to this kind of bending as a bending moment. The next kind of error that we typically see is concentricity. So our grips may be parallel, but they are offset. So what this is going to do is going to create a worse kind of bending error or bending moment that creates this S-type bending. So now we actually have regions of positive negative strain occurring in the specimen. And if our specimens are shorter, then we're going to see an even increased effect on the bending moment of those specimens rather than if they were longer within that load string. So why is this all important to our testing? If we go to our next slide, so we have an example of our specimen that has an angularity error. We have that higher strain side on one side and the compressive strain on the other side. And I'm actually gonna talk about metal for a second. So with metal, it is an isotropic material. It's going to carry the load on the positive strain side. And then after we've reached our yield, it's actually going to redistribute that load. So what that does is that if we're misaligned with a metal piece, our modulus our modulus is going to be affected and our yield is going to be affected. So our elastic region is affected. But once we've hit the plastic region, our ultimate tensile strength and our ultimate strain are actually not affected by that misalignment because we've been able to redistribute that stress within the specimen. If we have a composite that is misaligned, composites are very sensitive because they're typically brittle, they're typically low strain, and if you have fibers aligned in a certain orientation and you've already pre-strained those fibers, it's very likely that you've actually damaged the specimen when loading before we've even started the test. So we've created uneven stress strain distribution. We have some fibers that have started to fail in one region, and we're actually going to rapidly fail shortly thereafter. So we're going to have effects not only on our modulus and yield, we're actually going to see effects in our tensile strength and our ultimate tensile strain, accounting for, so we're actually going to see like worse results within our composites if we are misaligned. And we have an example of how significant this can be. So a couple of years ago, we did an internal study where we loaded some composite specimens into a frame that we knew that the grips were not perfectly aligned. And you can see in the graph on the right, we have a pretty big distribution within the stress strain curve, as well as a pretty big distribution when it comes to that tensile strength and our ultimate tensile strain. Now, with we then aligned the frame, which I'll talk about later about how we do that. And we can see that deviation within that those curves is significantly lower. Our ultimate tensile strength as deviation is significantly lower. And we actually saw that our ultimate tensile strength increased 6% after we did proper alignment. And that might not seem like a lot, but that could be the difference between shipping or not shipping a product. And we also saw that our tensile strain increased as well. So certain industries mandate proper alignment, especially aerospace industries. And this is coming from NADCAP, or the National Aerospace and Defense Contractors Accreditation Program. So when it comes to metals, they require that ductile metal does not have more than 10% bending moment within that load string, no more than 8% bending moment in non-ductile metal, and no more than 5% bending moment in cyclic applications. When it comes to composites, they require that we have no more than 8% initial bending moment in the load string in order to pass compliance. So then how do we actually achieve alignment within our load string? Talking about grips, we recommend moving body wedge grips. So this pushes our jaw faces towards the specimen, providing repeatable jaw face engagement. We have a side-to-side symmetrical wedge pocket that controls the alignment as well. And then we want our body of our grip to actually be symmetrical front to back. So here we have hydraulic wedge grips as well as precision manual wedge grips. So there are some types of grips where they have a physical back to them. This is actually going to add weight to the grip and cause more bending moment within the load string. Even if it might not seem like a pretty significant amount, it can complicate getting your load string aligned and actually adding to the bending moment within the load string. So again, hydraulic wedge grips or precision manual grips we recommend. And then very simply, you can use specimen stops within your grip space. And we have a video to show how those are used. So a specimen stop is a very simple design that you can screw onto your jaw faces or maybe your grip body. You would take the width of your specimen and then place the top and bottom alignment stops in your load string. And not only does this mean that you're ensuring the same placement every time and that you're getting proper alignment, it's honestly just way easier to load into the load string. It's not as awkward having to hold your arm in place in one spot. So next, I'm going to talk about the system itself. It's no good having a rigid load string if the system itself is not rigid. So we want to make sure that we're using precision designed and built frames that are guided and have high axial and lateral stiffness. Our 6800 series of frames have been designed with this in mind, with large diameter ball screws, thick columns, and then a nice thick steel crosshead. And not only is that contributing to our alignment, but we want to make sure that the frame can actually handle the wear and tear of composite testing and those high energy breaks that we might be seeing over and over and over again. And then furthermore, we can add an alignment fixture to the load string. So here we can see our version of an alignment fixture called an Align Pro. It sits permanently in between the load cell and the crosshead. And there are 8 set screws on the Align Pro, and you can adjust these to adjust for your angularity and your concentricity. And in the next slide, we actually show the effects of adjusting those. So alignment, when we do alignment, typically what you do is you take an extremely stiff specimen with strain gauges, reading the top, middle, and bottom bending moments of your specimen. You load up your frame, and then you can read what the actual bending moment is occurring within the specimen itself. So there we show, Stefan is showing, we have a top, middle, and bottom bending moment. And as the field service engineer or as an accredited, somebody accredited within alignment is adjusting the Align Pro, we're seeing the change in that bending moment actively happening. And this software also suggests what to do to actually achieve like the best or the lowest bending moment that we see within the load string. So down at the bottom, it shows the suggested actions of unscrew -Y, screw in +Y. After you've had your load string adjusted, or even if you don't get your load string adjusted, you do have the option to have this reported out and you can use for your lab's accreditation or just your records. So looking at compression, so we talked about tension. For compression, we typically use compression platens that have locating rings and very strong surfaces that can, again, handle the wear and tear of testing over time. And we recommend putting a spherically seated compression platen on top and a rigid compression platen on the bottom. So you drive your platens together, and once they're perfectly parallel, you would lock in the spherical seat, and this actually meets the NADCAP compression alignment requirements. And then when you're doing any kind of compression testing with a fixture, like with the variety of fixtures that Stefan talked about earlier, we want to make sure that these are also laterally stiff and well guided, and then sitting in between those parallel compression platens. And the guidance is now actually going to come from the fixture itself rather than the machine. But these are also okay for alignment as well as NADCAP. So this is kind of a twofer slide when it comes to alignment and also as productivity. So let's say your load string's been aligned with tensile grips, or if you're using tensile grips that are just very heavy and cumbersome, you might not be able to remove the tensile grips from your space. And if you're aligned, you actually cannot do that, or you're going to negate the alignment that you had just done. So you want to take advantage of piggybacking. So on the left, we have some examples of piggybacking with the precision manual wedge grips inside of a chamber system, which I'll talk about next. And then on the right, we have even more variety of tests that we're showing for shear, flexural, as well as compression, of course, showing that we're capable of piggybacking within extended hydraulic wedge grips that are also going into a chamber system. And I'll finish with this slide saying that if you are using a chamber, you want to double check that the temperature rating of the fixtures is okay for the desired temperatures that you are testing to. So let's say you're using temperature chambers. These can typically do both high and low temperature testing. For heating, we're going to use electrical heating and air circulation for uniformity within the space. And then for cooling, we're going to either use liquid nitrogen or carbon dioxide, which takes temperature down to about -150 Celsius. For long-term testing or creep testing, you we recommend that you look into using mechanical cooling or refrigeration type systems, which typically other companies can handle. When it comes to humidity testing, if you could go back just one, Stefan, thank you. As Stefan said earlier, specimens are commonly conditioned prior to testing under humidity, but they might take a long time to come to equilibrium. And so testing can typically be safely done at non-ambient temperature only. In some cases, humidity may be required for long-term creep or fatigue testing, which again, we recommend looking at humidity systems with third parties. Instron does not offer any kind of long-term humidity systems. So I've talked a lot about the testing itself, and Stefan's obviously shown a lot of variety of testing that can happen. So I want to touch on the software portion and actually managing those tests within the software that you test with. So at Instron, we have Blue Hill Universal. We provide a composites module that actually comes with a variety of common standards, ranging from tensile, compression, flex, shear, etc. And these methods have been made to their associated standards. And it's very easy to take one of these pre-built methods and then modify them and actually save them locally to Blue Hill and do what you want. Or you could create methods from scratch. So if you are making changes to methods, whether you're using a pre-built list or whether you're creating from scratch, Blue Hill Universal does come standard with revision history. So this automatically tracks any changes that you're seeing in your method or any changes you're seeing within the sample file itself. So here is an example of the revision history from a method file. We get the action that occurred, the item that was affected, the new value, and then the previous value. So this just helps keep track of changes in the background so you don't have to worry about it. And then lastly, Blue Hill is available on Windows 11 compatible touchscreens, and these do mount to the frames itself. So what this means is that you're not having to input any values or start the test from like a different desktop you have to walk over to. We're keeping everything within one cell, so it's nice and ergonomic. So going back to NADCAP, NADCAP not only requires alignment, but they also will perform audits, including auditing documentation, procedures, but also maybe you're doing your own kind of auditing internally. We have options for helping with auditing. We have a traceability option within Blue Hill, and this is fully NADCAP audit compliant, and there's two main features to traceability. The first one is the audit trail. So this is tracking your logins, your logouts, and any kind of deletions. And essentially, it's tracking any major keystrokes that are happening on the system itself. This is all stored in a SQL database, which can then be searched through or filtered through and easily pulled up for those audits. And then the second aspect that we have with traceability is electronic signatures. So this is totally optional. But if you wanted to have sign-offs done on method changes or on sample file reports or report outs or report changes, you can have these signatures done at the system rather than having to print out any documents and get them physically signed or tracked. So this keeps track of any changes that are made. You can do 1 or 2 levels of sign-off before you release the method. And then let's say you have a lab with a bunch of frames, and we have something that's akin to a lab management system called Blue Hill Central. So Blue Hill Central connects all of your frames to one network, and your methods and sample files can be viewed in an office or at a personal location. So if we hit next, we actually have a nice animation of this. So we have our laboratory with all of our frames. Those are outputting any test results to the office. And then if the office wants to make any changes to methods, let's say the frames are all running the same method, rather than going to each individual frame and like making the same change to every frame, or like taking a USB and plugging it into every frame, you have the option to make the changes in your office location and then push it to the laboratory. So all the frames are using the same methods, report files. So again, just to reiterate, we're getting all of our data sent to our office, and we're getting any kind of like major changes pushed to our laboratory. So everything is similar and the same. So.
All right. Thank you very much, Ashley. In the interest of time, I'm going to try to cover this real quick because we do want to try to answer questions for you. So future trends real quick. So we do see adoption in different industries now. We also see a lot of recycling. SGL Carbon, for example, just announced a partnership with Carbon Cleanup for auto composites. We do see more thermoplastic and also natural fibers. We might see some through thickness reinforcement, and there's always manufacturing technologies that are evolving. If you go to a major trade show, you'll see a lot of 3D printing additive processes. And of course, we might see some AI here, I would think, maybe for analyzing large data sets and summaries for that, as well as more modeling and probably still more testing to determine base properties of your composites. And with that, I'd like to move into the Q&A section of the webinar.
All right. Thank you so much, Stefan and Ashley. That was great. We have questions, so let's move through those. One of the first ones we got is, what is the best option for high temperature tensile compression testing? And he gives the example of 260 degrees C, or they give the example, of reinforced polymer composites. Do you use a strain gauge or a video extensometer?
Yeah, that's a good question. It really depends on what testing standard you're following and if the video extensometer can achieve the required precision and accuracy requirements of the standard and the ASTM or ISO classification, really. So depends on the video extensometer. But yeah, strain gauges are always still used a lot.
What kind of applications require testing of the Poisson's ratio?
Yeah, I mean, if you really want to fully determine the properties of your material, then that is something that you'll have to do. You'll have to measure the strain on the axial and transverse direction within the same test to determine it. And it is, for example, in ASTM D3039, it is optional in there, but if that is a desirable, then that is one that you can follow. And then also ISO 527-4 and 5. Although they do refer back, I think, to the original -1 and so on, but they do also have a section on the Poisson's ratio. So it's, if you want to fully determine your properties, you do need to run that test.
What does tapered 45 degree and 90 degree mean in ISO 527/45?
I mean, it depends if this is now referring to there's some new test specimens that kind of like recreate a bow tie shape. It might be related to that, but it might also be related to the tapering angle of the tabs that you're using. So if you're adding load transfer tabs, there's typically some recommendations or requirements on what shape they need to have, and then and their tapering, and so it might be related to either of those two. I mean, we need to have a little bit more detail about the section within the standard, but that's usually what I associate with that.
So I would suggest for everybody, and I'll say this again when we wrap up, that you reach out to Stefan and or Ashley when you have these kind of questions too. In compression testing, what is the impact of the length of the specimen on the results?
The impact of what?
The length of the specimen.
Not sure what's meant with that. I'm not familiar with that term. Ashley, have you
In the compression testing?
The length, Stefan.
Oh, the length of the specimen?
Yeah, in compression testing.
I mean, it's not like that I have run so many with different lengths that I could tell you any kind of difference there, but I do know that there's recommendations of either minimum length or also maximum length, and it really depends on which one you're following and what they are allowing, and then what kind of fixture you're using. But usually you're very much tight to the fixturing that you're using, and there's really only so much of a range. And I would also always for such questions, one good thing to do is at least within the ASTM standards, they usually have a section that is called interferences. It's typically pretty far up. You usually have like section 3 is usually like the terms within the standard, and then after that there's like a summary, and then usually it goes into the interferences section, and that usually tells you a lot about what kind of events or ways of making your specimen and all those kind of different things, how you can run the test, actually affect your results. So that would probably be a good section to look at. But in general, the length is kind of required within the standards, and they give you either a range or a fixed length that you have to use.
I want to comment on that too. So some standards too require a minimum length, because I've seen some standards where if you have too short of a specimen, your strain is so tiny, it's almost impossible to get like an accurate value. So as Stefan said, refer to the standard, but also be careful that you're not going too small, or else it's going to be very difficult to actually get values that you want to find. So.
Yeah, that's a great point. And just to add to that, now you kind of reminded me of that. That's a good point, because the longer your specimen, like we talked a lot about alignment and bending and all that stuff. So the longer your specimen, the lower those effects of that will be, right? So if you have a shorter specimen, any kind of misalignment will be, the arrow will be much larger on a shorter specimen, and therefore also the effects of that misalignment will be more significant than as if you made your specimen longer. Yeah, so that's a great point, Ashley.
We have 2 more questions we're going to try to get to. Why are strain gauges the only way to measure the strain for a compression test?
Yeah, it's a great question. Just, I would say look at the fixturing. Like if we think about any of those, that Italy fixture from ASTM D3410 or that combined loading from 6641, there is not very much space. You usually need to have for 6641, I believe I remember that the free section between the upper and the lower part of your specimen is supposed to be 13 millimeters, so just about half an inch, which is really short, and it's almost impossible to. I mean, it would be a half inch. I mean, you wouldn't even be able to get a half-inch gauge length with any kind of extensometer in there, right? Because like the free section is only that short, and there's just no space. And then the other thing is also you need to be accurate enough, and you also in those compression tests, I would have to review the standard in detail again, but at least for the first 5 or 7 tests or so, until you can prove that you don't deal with too much bending or misalignment, you actually need to use strain gauges on both sides of the specimen, and then prove that your strain readings are within 10% of one another. So all of that is determined in the standard. So for any anybody who needs to follow it, read it in detail. It's all explained in there. But those are all part of the reasons why you need to use strain gauges. It's physically not really possible to use something else, and at the same time it's also just required within the standard if you need to follow it, and you need to prove that you don't have too much bending within your specimen. So there's quite a few reasons for it.
Okay.
Stefan,
really
it might be
quickly,
I would say it might be worth going to the next slide, because we did do a whole webinar on strain with Composites World. So that's on our YouTube, and then I believe you can also find it through Composites World or scan the QR code. So
thank you. That's awesome. One last question. Is misalignment ever used on purpose in order to simulate specific use cases when testing, for example, simulating curved CFRP skins?
That's a really interesting question. I'm not aware of that. It's also, I got to be honest with you with that question also. I mean, it's a great question, because people typically that make composites and they test them and that buy equipment from us, it's kind of everybody's secret sauce, and nobody really wants to give it away. So it can be really difficult for us sometimes to also find out what is actually being done or what do people do. I've not heard of that yet. It sounds interesting. I mean, you might be able to kind of simulate a worst case scenario in your end application that way. But I'm not aware of anybody actively doing that, but I can imagine that could be helpful.
All right. As we wrap up today, I would like to give 2 suggestions. One, let us know. Let Instron know what topics you guys want to hear about in the future. let Composites World know as well. We can see that you guys are really interested in testing, and we want to know how to better meet that need for you. And also, send us your best practices. I think Instron would be curious to hear what you guys are doing, and it could be an interesting dialogue. But we really appreciate the great presentation and the great interaction today from Stefan Batsky and Ashley Davis from Instron. We invite you to reach out to them. And we also want to thank all of you for being here with us today. We are glad to have you involved in these webinars, and we hope to see you again soon at the next Composites World webinar. Have a great day, everybody.